This video starts by translating a balanced equation into normal English, and then I use that language to first define, and then demonstrate in the lab, the 6 categories of chemical reactions classified by matter. Hello, Chemist Corner. Today I want to translate from chemistry into English. You might recognize that as a balanced equation. In fact, it's a sentence. It's actually a sentence describing my reactants and my products. So what I want to do is simply translate what you see in front of you from chemical symbols into proper English. What I have written in green, those are my reactants. What I've got written in blue, those are my products. The green arrow is not really an arrow. What it is telling you is there's a reaction taking place. That says these react to produce the products. Sometimes we say yields or just produces, but that's telling you a verb. That is telling you an event has taken place. My red numbers here, my 2 and 13 and 8 and 10, those are called balancing coefficients. And my balancing coefficients tell me the ratio in which these two compounds react. My butane and my oxygen react in a 2 to 13 ratio. For every 2 molecules of butane, I need 13 molecules of oxygen. Now, in my previous video, I talked about moles, and my balancing coefficients actually become the mole ratio. So I can retranslate that to say 2 moles of butane molecules react with 13 moles of oxygen molecules to produce 8 moles of carbon dioxide and 10 moles of water molecules. Those little g's, they're a subscript. They are telling you the phase. They are the phase subscripts. And we have several phase subscripts that we often use in chemistry. G refers to gases. L refers to liquids. If it's a solid, little s. And that seems like it, solid, liquid, gas. Well, not quite. If you have a solution, something dissolved in water, we would use AQ to say aqueous, dissolved in water. Maybe it's not dissolved in water. Maybe it's dissolved in alcohol. If it's dissolved in an alcohol, we use ALC to indicate my solvent is an alcohol. I do a reaction with my grade 12 students in which my solvent becomes ammonia, so we use AM. So there are many different phase subscripts, although the most common, of course, solid, liquid, and gas. Now I can almost translate this. There are 2 things left. My plus sign is actually telling me the reaction. These react. And I've got platinum written over the arrow. Well, it's not a reactant. It's not a product. It's something else. It's something that helps the reaction proceed faster without being consumed as a reactant, without being produced as a product. My platinum is called a catalyst. Now I've got the language to translate. Here's what it should say. 2 moles of butane molecules in the gaseous phase react with 13 molecules of oxygen gas in the presence of a platinum catalyst to produce 8 moles of gaseous carbon dioxide and 10 moles of gaseous water. That is the language of the balanced equation. Now that we have the language of the balanced equation, now we can use that to classify certain chemical changes. Now, I'm going to go through 6 different classifications. These are not the only classifications. They are simply the most common ones that we use every day. The first one is a synthesis reaction. A synthesis reaction is when 2 or possibly more reactants react together to form a single product. I'll show that in just a generic form of saying this. A plus B, as my reactants, react to produce a single product. That would be a generic synthesis reaction. Here is a specific example. If I take magnesium, solid, react it with oxygen gas, that can produce the product magnesium oxide, which will be a solid. To balance this equation, I need 2 oxygens, so I would put a 2 there, which gives me 2 magnesiums. This now says 2 moles of solid magnesium metal react with 1 mole of gaseous oxygen to produce 2 moles of solid magnesium oxide. Let's look at that. The synthesis reaction I will do today is the reaction of magnesium metal with oxygen gas to produce magnesium oxide. Magnesium metal is shiny and silvery like most metals are. But in order to react it with oxygen, we have to put in a lot of energy to break those oxygen bonds. So that's why I have my Bunsen burner. The magnesium burns with a very bright light, and the product, as you can see, is powdery. It is crumbly. It's no longer a malleable, ductile metal. It's a powdery salt. The second kind of reaction that we're going to talk about is a decomposition reaction. In a decomposition reaction, I start with a single reactant. The single reactant breaks down into 2 or more products. Again, the generic form would look like this. A compound of some sort breaks down into 2 products. Now, my products could be elements, they could be they could be compounds, either or. A specific example, I could use hydrogen peroxide. We can buy hydrogen peroxide in the supermarket, about a 3% solution. That will decompose into liquid water and gaseous oxygen gas. To balance this, I have 2 hydrogen peroxides, 2 waters, and 1 oxygen gas. That will happen spontaneously over time, just sitting in your medicine cabinet at home. However, it goes a lot faster if we put in a catalyst such as manganese 4 oxide. Let's take a look at what that one looks like. The decomposition reaction I'm about to do is aqueous hydrogen peroxide decomposing into liquid water and oxygen gas. However, this reaction is very, very slow at room temperature. Here's hydrogen peroxide you can buy in any grocery store or pharmacy, and it's simply a clear, colorless liquid. The decomposition reaction is so slow at room temperature you can't even notice it. However, with the addition of the manganese 4 oxide, just a little catalyst will speed up this reaction so that we can actually observe it. The decomposition of hydrogen peroxide is also sped up by the addition of blood, but I'm not going to bleed into it today. Immediately it starts to fizz, and with a little stir, we can see lots of bubbles forming, which is simply oxygen gas being produced. That's the decomposition of hydrogen peroxide. The third kind of reaction we're going to look at is the single replacement. A single replacement is any reaction in which an element reacts with a compound to produce a new element and a new compound. I can replace either a metal or a non-metal. So I can look at this. My generic form, A plus BC equals AC and B. In this case, I've replaced the metal with a different metal. Another possibility is if I replace the non-metal. In this case, C would be the non-metal. I've replaced it with A. That would be a non-metal replacement. Here's a specific example. I can take the element calcium, solid metallic calcium, and react that directly with water in the liquid form. In this case, calcium is a metal. It can remove hydrogen from the water and produce calcium hydroxide precipitate. It will be a solid and generate some hydrogen gas. Again, if I want to balance that, I need 2 waters. For every 1 calcium, I will use 2 waters. That will produce 1 calcium hydroxide and 1 mole of hydrogen gas. Of course, hydrogen gas is flammable, explosive if you have enough of it. So that can be lit on fire as a test to say, yes, I am producing hydrogen gas. Let's take a look at this reaction now. A single replacement reaction is a reaction between an element and a compound to form a new element and a new compound. The compound I'm using today is simply distilled water. So I'll put a little bit of distilled water in my beaker. And to show the effect this reaction has on the pH of the overall system, I'm simply going to add a little bit of phenolphthalein, a little bit of acid-base indicator in there. My element, I'm going to use calcium. And calcium is a shiny, malleable, ductile metal which corrodes very, very quickly in the presence of oxygen. You can see the color is turning pink. That is evidence for the production of hydroxide ions. As well, I'm producing a lot of gas. That gas is hydrogen, and I can show that by burning it off. The bubbles are very, very, very flammable. The phenolphthalein turns the color pink in the presence of hydroxide. The gas is hydrogen gas. And the white that you see there is the calcium hydroxide solid being formed. So not only have we produced bubbles, we produced a precipitate, a white precipitate of calcium hydroxide. My fourth kind of reaction is going to be the double replacement. We just did the single replacement, now a double replacement. In this case, a compound reacts with a second compound, and it produces 2 new compounds. This is almost always talking about ionic compounds reacting with other ionic compounds. The generic form would look like this. If I have AB reacting with CD, I'm going to doubly replace. That is, I'm going to replace A, the first metal, with C, the second metal. At the same time, I'm going to replace B, the non-metal, with D, the nonmetal. So that becomes AD and CB. Remember, in ionic compounds, we always write the metal first. We always write the nonmetal second. A specific example of this could be a nickel chloride dissolved in water reacting with a sodium hydroxide dissolved in water. That would now produce a sodium chloride, which will be water soluble. It will dissolve, so we use the AQ as a subscript, and nickel hydroxide. And since nickel has a 2+ charge, I need 2 hydroxides. Nickel hydroxide has low solubility in water, and so that will be a solid. To balance this, I need 2 hydroxides, so I need 2 in front of the sodium hydroxide. That requires 2 sodiums, 2 sodium chlorides, and it is now balanced. Let's take a look at that very simple reaction. Nickel 2 chloride reacting with sodium hydroxide. We should see a colorful precipitate as a result. Double replacement reactions are reactions between 2 compounds that produce 2 compounds, usually ionic compound with ionic compound, to produce an ionic product and a second ionic product. The reactants I've chosen for today, we're going to use nickel chloride, which is a green powder, and some sodium hydroxide, which I can just pour a little bit in. I'm going to dissolve both of those in water, so I will add a little bit of distilled water to my sodium hydroxide and to my nickel 2 chloride. Give it a little stir to make sure it's well dissolved, and again a little stir to make sure it's well dissolved. When I combine them together, I expect to see a solution of sodium chloride and a solid of nickel hydroxide. So there's my sodium hydroxide, add the nickel solution to it, and sure enough I get a very gelatinous kind of gooey solid there. You can tell there's a solid because the light has been scattered. It's now translucent, it is not transparent. That is evidence for a solid suspended in the liquid. My fifth kind of reaction is called a combustion. Combustions are sometimes called oxidations, and you'll see why. A combustion is when any element or compound reacts with molecular oxygen, that is, oxygen in the form of O2. Not in the form of O3, that would be ozone, and that's a different reaction. So it's any element or compound reacting with O2, and it produces only oxides. So the only thing on the right-hand side of the equation will be oxides. There are 2 very different types of combustions. I can have metallic combustion where a metal reacts with oxygen and it will produce a metal oxide. Those tend to also be synthesis reactions. I can have a hydrocarbon, such as methane, reacting with O2, and that will give me 2 products, the oxide of carbon and the oxide of hydrogen. My oxide of carbon is carbon dioxide, and the oxide of hydrogen, of course, is simply water. If I balance that, I need 4 hydrogens, 1 carbon, and 1 oxygen. Well, that doesn't work. I need 2 oxygens. A specific example of metallic combustion is one that I really enjoy doing, and that is burning iron. So I start with elemental iron, a solid, reacting with oxygen gas, and that will produce iron oxide, specifically iron 3 oxide. So the formula will be Fe2O3, and that will be a solid. Oh, and that's it. That's the only product. Because again, if you have a metal combustion, you tend to get a synthesis reaction. To balance this, I need an even number of oxygens on both sides. So I need a 2 in front of the iron 3 oxide. That gives me 6 oxygens, and that gives me 4 irons. Let's take a look at that reaction in my Bunsen burner flame. Combustion is simply any element or compound reacting with oxygen to produce only oxides. In this case, I'm going to burn iron, but my Bunsen burner is already a combustion. It is simply a hydrocarbon combustion. If I take simply iron filings and shake it into my Bunsen burner flame, you see metallic combustion as well as hydrocarbon combustion. The last reaction I'm going to do today is called an acid-base reaction, sometimes called a neutralization. An acid-base reaction is simply a reaction between an acid and a base. Most of the time we define an acid to be an ionic compound that contains the hydrogen ion, that is the H+ ion. And a base, an ionic compound that contains the hydroxide or the OH- ion. Now, I understand that not all acids contain H+ and not all bases contain OH-, but this is a simplistic way to approach an acid-base reaction. The generic one is simply this: H together with any anion, that would be my acid, reacting with any metal with hydroxide. If that's my setup, then my base, my metal on my base, is going to combine with the X, and I'll end up with my salt of Bx. My H+ from my acid is going to react with the OH- from my base to produce water. And I'm going to write it as HOH to indicate that, yeah, the first hydrogen came from the acid, the OH came from the base. The most common acid-base reaction we do in the lab is hydrochloric acid dissolved in water reacting with sodium hydroxide, also dissolved in water. If I do that, my sodium from my base combines with my chloride to make a soluble compound of sodium chloride and, of course, liquid water. This one is very easy to balance. It's all 1 to 1 to 1 to 1. Unfortunately, when we do this, both hydrochloric acid and sodium hydroxide are clear and colorless. So we often like to put an indicator in my solution to see when is this reaction complete. And that's what we're going to do next. I'm going to start with some distilled water and just add a little bit of universal indicator to indicate the pH at the moment. Give it a little swirl to give it a good mix, and you can see we're at a neutral pH. That color indicates neutral pH. I'm going to add a little bit of base to basify the system. And you can see the color has gone from a green to a bluish color. If we add a little bit more base, we might be able to get to purple. All right, that's as far as we're going to go with this concentration. Now I'm going to add some acid from my HCl. and watch the change. We're back to neutral. Just a couple more drops. Give it a swirl. Oh, we're still at yellow. Add 3 or 4 more drops. And you can see we're trying to get to the red color. We're kind of orangish right now. Add a few more drops of dilute hydrochloric acid, and there we have the color of the acidic solution. That's how to make acid-base reactions a little bit more colorful with the universal indicator. If you found this video useful, interesting, or even entertaining, like, comment below, subscribe, and check out some of my other videos. See you again in Chemist Corner.